Okay, let's continue our study of elliptic curves. So we'll remind you of the definition we did last time of the elliptic curve. Look at the properties of the addition law. So addition is commutative. There will be additive inverses. We introduced the additive identity element. That was the p infinity element. Then we're going to find a formula for calculating the sum of 2 points on the elliptic curve, or for doubling a given point. Then I want to look at the associative law. So you'll recall, in order to form a group, we need a binary operation that's closed, that has an identity element, has inverses, and is associative. And it turns out that the associative law is the real hard one for the elliptic curves. And I want to give you 3 points of view for proving it. Then we'll just take a brief look at some facts about the rational points on elliptic curves. These will be topics that are beyond the scope of the class, but they're very interesting theorems. So Delos Theorem and the Lutz-Nagel theorem. And as well, I want to talk briefly about the rank of an elliptic curve defined over the rationals. So what was our addition law? Take a generic elliptic curve of this type. Then if I give you 2 points on the curve, we define a plus b to be the reflection of the point AB through the x-axis. So you'll recall the elliptic curve may look like this, let's say. And if we have A and B, 2 points, draw the line joining A and B. This point is called AB. Reflect that. And this was the sum, A plus B. So let CF be an elliptic curve with point at infinity, P infinity. Then we claim that P infinity is in fact the zero element of the curve with respect to the addition law given. 2, addition of points on the curve is commutative. And 3, every point has an additive inverse. So if xy is a given point on the curve, then the opposite of that point is x comma negative y. So again, let's draw a picture over here. Of a typical elliptic curve. Something like that. And let's look at property 2 first. So if I look at A plus B, so here's a point A and here's a point B. And I say, well, what's the definition of A plus B? That would mean AB P infinity. So here's AB. And down here would be AB P infinity. The reflection of AB through the x-axis. Okay, so that's that point. Whereas B plus A is BA P infinity by definition. Well, where is the point BA? Well, BA means draw the line segment joining B and A and find the third point of intersection. Well, that's exactly this point. So AB and BA are exactly the same point, and therefore we get exactly the same value out, A plus B. And that's all there is to the commutative law. P infinity is the zero element. Okay, so let's take a given point A, and I want to add to it P infinity, and I only need to do it from one side now that we know that it's an Abelian law. So this means A P infinity, P infinity. Well, what does A P infinity mean? That means draw the vertical line through A and intersect it with a curve, and so you get this point. Let's call it A prime down here. So that's A prime P infinity. And what does A prime P infinity mean? That means draw the vertical line through A prime and intersect it with a curve. And when you do that, the new point of intersection is the value A. So this is just returning us to A. So A plus P infinity is equal to A. And then finally, let's show that every point has an additive inverse. So if P is my given point right here, xy, and I add to it this point right here, which is, let's call it for now P prime, same x, and the y coordinate is the opposite. Okay, what do you get when we add those 2 points? P plus P prime. That means P prime, P infinity. Now P prime means draw the line joining P and P prime, and that's certainly a vertical line. And the other point of intersection would be the point at infinity. So this is just P infinity, P infinity. And then again we have a convention that P infinity means P infinity. So P infinity is an inflection point. And so we see that P plus P prime is P infinity, which is the identity element of the group, and therefore P and P prime are additive inverses. P prime is the opposite of P. QED. So we finished all 3 parts. Next, let's find a formula for calculating the sum of 2 points on an elliptic curve. So again, start with the generic equation. Let P and Q be any 2 points on the curve with distinct x coordinates. And let's find the formula for P plus Q. So I draw the line joining P and Q, and let's say its equation is y equals mx plus k. Then the slope m is trivial. That's just delta y over delta x. And the value k would be y1 minus mx1. And calculate that. So the slope is y2 minus y1 over x2 minus x1. Put a common denominator down here. And when we simplify, something cancels out. The x1, y1 and the plus x1, y1 will cancel out, leaving us with y1, x2 minus y2, x1. Okay, so we get those formulas. Next, let's intersect that line with the curve. So when we intersect the line in the curve, y equals mx plus k with y squared equals the cubic curve, x cubed plus ax squared plus bx plus c. So we get mx plus k squared is x cubed plus ax squared plus bx plus c. And then turn this into a cubic equation. So I get 0 is x cubed plus a minus m squared x squared plus b minus 2mk x plus c minus k squared. All right, so I need to solve this cubic equation for x, but I know two of the solutions. So x1 and x2 are given solutions to this equation. And what we also know is, okay, and then x3 is the third solution. So what we know is that the x squared coefficient is the sum of the three zeros of this polynomial. So x1, x2, and x3 are the zeros. And so x1 plus x2 plus x3 has to add up to the opposite of this coefficient, which would be m squared minus a, and then we just solve for x3 to get m squared minus a minus x1 minus x2, giving us this formula up here. And then y3 is trivially given by this. That's just the slope. y3 minus y1 over x3 minus x1 is the slope, m. And so using this formula, we have an easy way to calculate the third point of intersection when we draw the line joining P and Q. So first we find the slope, then we calculate x3 using this formula here, and then we calculate y3. And that gives us P plus Q to be x3 comma minus y3. We then reflect the point through the x-axis to get the sum P plus Q. Now to get the sum of a point with itself, so if x1 and x2 are equal, let's say we have P equals Q equals x1, y1, then we can just use a limiting process to find the formula. So we don't have to go back to scratch here. So let's assume that the tangent line at P is not vertical. So that would mean that y1 does not equal 0. Then we can obtain P plus P by letting Q approach P. So let Q be a point with a distinct x-coordinate and let it approach P in the formula we just calculated. So as Q approaches P, the slope of the secant line joining P and Q will approach the slope of the tangent line. Exactly what we do in calculus. And what is the slope of the tangent line? Well, our equation was y squared equals x cubed plus ax squared plus bx plus c. So 2y prime is 3x squared, like that. And so y prime is this quantity over 2y1. So that's where the slope formula is coming from. And so if we take the equation on the previous page and just plug in this value for m, the value m is approaching, you would get that x3 is m squared minus a minus x1 minus x2, but x1 and x2 are now equal to x1. And then y3 is as given before. So let's look now at the associative law. That's all that's remaining to show our binary operation forms a group. So we claim that given any 3 points on an elliptic curve, CF over R, A plus the quantity B plus C is the same as A plus B plus C. And as a consequence, we conclude that with the addition law as defined above, the set of points on the elliptic curve form an abelian group with respect to this law. Now I want to give you 3 different points of view for understanding the associative property. I mean, all can be made into rigorous proofs, but we're just going to be very sketchy right here. So one approach is just to do brute force. So we've just established formulas for how do we form A plus B, or how do we form A plus A. So you can then do that calculation a second time and get an explicit formula for A plus B plus C, or for A plus B plus C, and just simply check that you're getting the same value coming out. So note that if we start with 3 points and we form this quantity A plus B plus C, you're going to end up with an expression that's a rational function in these variables, x1, x2, x3, y1 through y3. And one little trick you can observe, we know that the addition law is commutative. So this quantity right here is the same as this quantity. And so I need to show then that B plus C plus A is the same as A plus B plus C. In other words, if whatever rational expression I got in the first calculation for this quantity, I want to show that I get exactly the same quantity coming out if we substitute x1 to x2, x2 to x3, etc. So we're now calculating this quantity right here. And then of course we have relations that the xi's, yi's satisfy the elliptic curve equation. So we want to show that you get the same rational function modulo the ideal generated by those relations. So for instance, this is what the x coordinate looks like if you calculated A plus B plus C. It's a big hairy mess like that. And you can continue doing the same thing for the A plus B plus C, but it's a very tedious process and it's not very informative. That, well, okay, so these quantities happen to be equal, but why is it working out? So it's rarely do people proceed in this way to prove the associative law. The high road for proving associativity is beyond the scope of this class, but it's a very elegant way. So what you do is you make use of the Weierstrass elliptic function P of z. So this is a doubly periodic function on the complex numbers, and it's periodic with respect to a lattice of points. So the set of all integer linear combinations of 2 fixed complex numbers that are linearly independent over the reals, so omega 1 and omega 2. So you get this 2-dimensional grid of points in the complex plane, these dots like this, extending out indefinitely. Now this Weierstrass P function satisfies a differential equation that says P prime squared is 4 times P of z cubed minus G2P minus G3, where G2 and G3 are some constants depending on the lattice lambda. And this means that the point P prime P is a point on the elliptic curve defined by this equation. And notice that's the canonical form for an equation. There's no x squared term, but this is a pretty well a generic form for an elliptic curve. And you can show that this mapping that takes the complex number z to this projective point, P of z, P prime of z, 1, parameterizes the set of points on the elliptic curve in the projective plane over the complex numbers. And in fact, this mapping yields a group isomorphism between the additive group, where you take the complex numbers and you mod out by the subgroup lambda. Now this is a very simple abelian group. This is the complex numbers under addition, and you're modding out by this lattice, which is also trivially a subgroup of points. So this forms an abelian quotient group, and it is isomorphic to the group of points on the elliptic curve, where the group law is the geometric group law we have been talking about. Okay, so it's a very interesting approach, but it's for a deeper class on involving complex analysis and elliptic functions. So finally, there's a geometric proof that's both informative and, well, I don't want to say it's an easy approach. It requires certain theorems in geometry that require a fair amount of work. So I'm just going to again sketch the ideas. So the first observation is that a general homogeneous cubic polynomial in 3 variables is an expression of this type. So what I've done is I've written down every possible monomial that has total degree 3. So x squared y, x squared z, xyz, xy squared, xz squared. And if you count them up, there are 10 different monomials of total degree 3 in 3 variables. And so you can think of a cubic form as forming a vector space. So there's this 10-dimensional vector space of cubic forms with coefficients coming from the real numbers. And so I'll identify a cubic form with a 10 tuple of real numbers, a1 through a10, in R10. So now suppose we are given 8 distinct points in the projective plane, and I wish to describe all cubic curves, all homogeneous cubic curves passing through those 8 points. So each time you plug in one of those given points, I'll get a linear equation in the variables a1 through a10. So that gives me a system of 8 linear equations in the 10 variables a1 through a10. So if that system has full rank 8, so you've got 8 rows, 10 columns, if you have full rank 8, that's the biggest the rank can be, then the null space is of dimension 2. That's the rank plus nullity theorem. The rank plus nullity has to add up to 10. And you can show that, in fact, this is the case as long as the points that we started with, these 8 points, that no 4 of them are collinear and no 7 lie on a conic, a quadratic equation. So in those cases, you're going to find some dependency relationships between the 8 linear equations you've just formed. So it follows that, okay, so we have a null space of dimension 2. What does that mean? That means if you give me 3 points, 3 vectors in your space, in 3 vectors in your null space, that there has to be a dependency relationship between those 3 vectors. So if I give you 3 cubic forms, f1, f2, and f3, that vanish on a given set of 8 points, no 4 of which are collinear, and no 7 of which lie in a conic, that those forms must be linearly dependent. So there must exist real numbers lambda, beta, and gamma, such that lambda f1 plus beta f2 plus gamma f3 equals 0. In particular, if no two of the fi's are multiples of one another, so that these scalars are all non-zero, then any time you would have a common zero of two of them, so let's say that f2 of p equals 0 and f3 of p equals 0, well, that would mean that lambda f1 of p is 0, right, because these two vanish, but lambda is not 0, so f1 of p would be 0 also. And that's the important point we use for the associative law. Any common zero of two of three cubic forms must be a zero of the third one. Okay, so now back to our elliptic curve. Y squared equals p of x. Let's take 3 points, A, B, and C on the curve, and show that the associative law holds. So I'm going to form 3 different cubic polynomials. f1 is the elliptic curve y squared minus p of x. f2 is going to be a product of 3 linear polynomials. So in this notation, L of AB just means the straight line passing through A and B. Or rather, it's the linear polynomial having zeros at A and B. This would be the linear polynomial passing through BC and B plus C, and this is a linear polynomial of the line passing through A plus B and C. And then f3, you take this linear polynomial times this linear polynomial times this linear polynomial, and we get, once again, another cubic polynomial. Okay, now let's make 3 notes about these 3 functions I've just defined. So all 3 are cubic polynomials. Right, a product of 3 linear polynomials is cubic. Second, there are 8 points that are common zeros of all 3 of these polynomials. So A, B, C, AB, BC, A plus B, B plus C, and P infinity, they are all trivially zeros of the elliptic curve. Right? When you form A, B, and C are given points on the elliptic curve, these, by definition, are all points on the elliptic curve. F2, why are all these points on F2? Well, A and B are on this line. C is on the third line. AB is, well, where is AB? That's on the first line. This first line passes through A and B, and therefore also passes through AB. BC is on the second line. A plus B is on the third line. B plus C is on the second line. And where is P infinity? Well, you notice that this second line is a vertical line. BC and B plus C are just reflections through the x-axis, so that's a vertical line, and therefore it passes through P infinity. And you can do the same analysis for F3. So F3 also passes through these 8 points. And then the third fact I want to observe is that A plus BC is a zero of F1 and F2. So why is it a zero of F1? Well, A plus B is a point on the elliptic curve. C is a point on the elliptic curve. Therefore, this is, by definition, a point on the elliptic curve. And why is it on F2? Well, it satisfies, it's on this line. It's on the line joining A plus B and C. And then similarly, B plus CA is a common zero of F1 and F3. And so now you're getting the idea of where the associative law is going to come from. We're getting a zero, common zero of F1 and F2, and we're getting another common zero of F1 and F3. So let's continue. So we have to homogenize these three cubic polynomials. So I form capital F1, capital F2, and capital F3, and observe that they have these 8 common zeros. And then we make a further assumption that the 8 points are distinct, that F1 is irreducible. Well, that's given. That's our cubic polynomial in generic form, which is given to be irreducible. So since it is irreducible, it has no linear or quadratic factor, and therefore no 4 of the points on the curve are collinear, because if you had 4 collinear points, you would have some linear factor, and no 7 of them lie on a conic, otherwise you would have some quadratic factor. Thus, any common zero of 2 of these 3 forms must also be a zero of the third. And we have observed that A plus BC is a common zero of F1 and F2. Therefore, A plus BC must also be a zero of F3. But the only common zeros of F1 and F3 are the 8 we've listed above and B plus CA. Therefore, we get this equality. So A plus BC must equal B plus CA. This is the only remaining common zero we can have, and from that relationship we get the associative law. So what is this here again? This is A plus B C P infinity, and this means take A, well, you use the commutative law, so take B plus C A P infinity, and you observe, well, this quantity here and this quantity here are equal. And so you get the associative law coming out. So in the remaining few slides, I just want to talk about generalizations of elliptic curves and a few facts about elliptic curves over the rational numbers. So everything we've done so far can be repeated for a more general field. I've been discussing elliptic curves as though we were drawing them in the plane R2, so elliptic curves over the real numbers, but we could have been defining them over any field and made exactly the same definition for our addition law over any field. And again, you would find those same formulas coming out for how do we calculate the sum of 2 points on the elliptic curve, and so on. Okay, so let's talk briefly about rational points on elliptic curves and elliptic curves defined over the rationals. So there's just two theorems I want to point out. First is Delos Theorem, which says the following. If you have an elliptic curve defined by a cubic equation with rational coefficients, then the group of points with rational coordinates under the standard addition law we've been talking about is in fact a finitely generated abelian group. So repeating what we've done so far, you get immediately that it's an abelian group. What is new here is to discover that it's in fact a finitely generated abelian group. And when you study abstract algebra, what do you learn about finitely generated abelian groups? Well, you learn that they can be expressed as a direct product of cyclic groups. And as a direct product, some of your generators have infinite order, and so you have a certain number of copies of the integers. This is called the free part of the group. And then other elements have finite order, and this is called the torsion part of the group. And so any finitely generated abelian group can be expressed as the torsion part direct sum with the free part. And the free part is isomorphic to r copies of the integers, where r is called the rank of this group, or the rank of the elliptic curve, we call it. So one thing to observe is that the only time we have an infinite set of rational points on the elliptic curve is when the rank is strictly greater than 0. And if the rank is equal to 0, then we just have a torsion part of the group, and so we have a finite set of points, of rational points on the curve. Now, to find the torsion part of the group, we can use what's called the Lutz-Nagel theorem. So it says this: if we have an elliptic curve defined by a cubic equation where a, b, and c are integers, and I take a given rational point of finite order on the curve, then the claim is that x0 and y0 are both integers. So the only possible rational points of finite order are in fact integer points. And moreover, we can characterize what integers they can be. So y0 is either equal to 0 or y0 squared must divide the discriminant of this polynomial. A remarkable fact. So in the example we've been looking at, the elliptic curve defined by y squared equals x cubed plus 1, the discriminant is negative 27. So suppose that xy is a point of finite order on the curve with rational coordinates. Then if we look at the Lutz-Nagel theorem, either y is 0, well in that case x would be negative 1, or y squared must divide 27. And when can y squared divide 27? Well, that would mean that y would have to equal 1 plus or minus 1 or plus or minus 3. It's the only way a square of an integer can be a divisor of 27. And so we are only getting these other options. And so we get exactly the collection of 6 points we had before. The 6th point is coming from p infinity. And we found that we had a cyclic group of order 6. So the torsion part of G is in fact a cyclic group of order 6. Now it's still possible that there could be an element of infinite order, but in fact for this particular example it is known that these are the only rational points on the elliptic curve. There isn't going to be an element of infinite order here. So the rank is equal to 0 in this case for this particular curve. But again, that takes a lot more work to prove. The $1 million prize is understanding the rank of an elliptic curve. So this is one of the 7 Millennium Prizes listed by the Clay Math Institute, with a $1 million prize as the reward. So it's called the Birch Swenerton Dyer conjecture, Birch and Swenerton Dyer conjecture, and it states that the rank of an elliptic curve is the order of the 0 of an associated L function at s equals 1. So again, it's a very deep result studying L functions and the orders of the zeros.